Welcome to the lecture Digital 3D Documentations in Archaeology. Second part of the lecture Basic Aspects of Photo and Videogrammetry. Here we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. For photo-based 3D reconstruction, sufficient illumination and focusing of object details in the photos can be crucial. We have seen that feature extraction specifically looks for edges and image elements with different intensities. This knowledge is very useful right now to make good image acquisition decisions. So, to support feature extraction, we need to provide adequate illumination for all object details. Overexposure is also very unfavorable for feature extraction. Furthermore, well-illuminated parts of the image cannot replace missing focus in the image, so we have to pay attention to both aspects. For this, we once again hold as a rule to identify features and thus potential 3D points for 3D reconstruction. Relevant object details in the photos must be well illuminated and as well focused as possible. If the viewer can easily recognize structures or features in the photos, the computer usually can as well. It is often advisable to look at the distribution of the extracted features, because the number of identified features says nothing about the distribution within the images, as we could clearly see with the different example images and the resulting feature sets. On left, we see a concrete example of the serious influence a different illumination setup can have on feature extraction. In Illumination Variant 1, the focus was placed more on the upper inner area of the coin pot. In the image below, we can clearly see the distribution of the 30,000 features identified by reality capture with default setting. With Illumination Variant 2, the bottom was now additionally illuminated. The number of identified features has now increased to 50,000. If we compare both sets of points, two things stand out in particular. In Variant 1, the poorly illuminated bottom part is very sparsely populated with features, while the well-illuminated one has thousands of features there. On the other hand, there is a thinning of the features in the upper inner area from Variant 1 to Variant 2. Here we see the focus of the camera as the second important influence on the feature extraction. Due to the different illumination, the automatic focus of the camera was slightly changed. This also results in a significantly different distribution of features in the image. On right, illumination is not everything. Even more drastically, this example shows the influence of the camera focus. The sharpest area here is the front edge of the pot, while the rear area is very blurred. The distribution of the 46,000 features shows this influence very clearly. In the context of photogrammetry and videogrammetry, we must ask ourselves, which recording strategies do we have to pay attention to? We now want to take a look at a concrete example and discuss the important considerations for the capture strategy in this case. In addition to lighting and setting the focus, there is another very useful feature, the rule of 3, which we can derive directly from the 3D reconstruction. We can say an image feature must be uniquely identified in at least 3 images to be included as a 3D point in the 3D point cloud. The rule of 3 is indeed crucial for successful reconstruction. Only when we have visibility of a particular feature in at least 3 images, including those that capture the relatively hidden points within the relief, can that point have a chance to appear as a 3D point in the model. The rule of 3 is crucial for image acquisition and thus the basis for successful 3D reconstruction. Therefore, it is also clear that if we see, for example, a cube with its 6 sides and take only 6 photos of these sides, we cannot automatically reconstruct these images into a 3D model. As humans, we understand the structure of the cube and can do that, but the algorithms used here require sufficient image overlap, and that's where the rule of 3 comes in. So we have to pay special attention to the transitions of the sides to each other in the images. Now a brief overview will be given on the general recording rules that are most likely to lead to a successful 3D reconstruction result. First, photos should be taken as quietly as possible in good lighting because sharp images with good contrast lead to many good features. Second, each feature must be seen in at least 3 images, rule of 3, so the distance between the images in relation to the recording positions must not be too large. Third, the distance between the images in relation to the recording positions should be large enough for the features to be reliably determined, but not too large to ensure sufficient overlap of the image content. We can already see that points 2 and 3 contradict each other a bit. However, we will look at this in more detail in a moment in the context of videogrammetry under the aspect of the min-max problem. Fourth, recording the context around an object is important because points at the edge of a model are more prone to error than points whose position has been better determined by many surrounding neighbors. With the help of the rules just mentioned, we can better understand the common recording strategies and derive our own. Let's take a quick look at an example here. The relief structure of an Archaeopteryx lithographica is to be systematically recorded here. On the left, we see, in order to record the relief frame for a 3D reconstruction, it is purposeful not only to look at different angles of view on one axis from left to right, but to take these photographs on different horizontal axes. It is important that the photographs are taken quietly, well illuminated, and not in motion. In the center, we see that the rule of 3 is crucial for successful reconstruction and is applied here. Only if we see the relatively hidden points within the relief on at least 3 photographs, this point has a chance to appear as a 3D point in the model. On the right, we see the resulting set of the 43 shots. Below, we still see from left to right results of 3D reconstruction in reality capture, the mesh, the textured mesh, and a resulting orthophoto. You may wonder why capturing the context is so important in such a case. Here, we want to simplify and make clear why the inclusion of the context, meaning the area around the actual subject, is of great importance. We see a mesh of points in the upper left corner. Orange dots represent correctly identified points. In the middle, we want to make a point an error point and simply move it. In this example, since it has 6 direct neighbors who know its relative position to them, they would quickly realize that this point is faulty and remove it from the set of valid 3D points. The situation next to it would be somewhat different. Since there are too few neighbors at the points on the edge, we also have no reliable control mechanisms and leave faulty points sometimes as 3D points in the point cloud. But this means that points that are in the middle of the center are more reliable than points at the edge. As a consequence, we have to include a border, the so-called context. We can see this in the lower left picture. The orange points represent the actual reconstruction area that we want to reconstruct, and the area around it represents the context that we should include for this purpose. To the right, we see an example of the multicopters we will talk about later. Here we see the area A, which we want to reconstruct, and for this we take the larger area B. On the right, we see a practical example from Mongolia. Above, we see the point cloud with a very sparse border, and below that, the area that we can then reliably reconstruct from it. I would like to show 2 examples here that we captured in Mexico during a very early stage of the project in 2013. On the left, we can see a statue lying in the sand, and below it, a linen cloth with some inscriptions. The object was captured using videogrammetry and turned out excellently, despite the reflective surface. However, when we viewed the model on the computer after the trip, we were somewhat disappointed. Even though the cloth was reconstructed beautifully, the context below it was unfortunately not fully visible. A pity indeed. On the right side, the situation is a bit more drastic. Here, we have a 7-meter high sacrificial altar. No markers could be placed on it, but measurements were taken. Below, we can see images from aerial photography and the entire interior as a 3D model. Everything that was captured was reconstructed wonderfully. However, the downside of these captures is that we can only see one side, resulting in a textured 3D cloth rather than a complete 3D model. It was a bit time-consuming in hindsight to construct a version that could be, for example, 3D printed by extruding the model. Because it is so important, we would like to state the contextual recording here once again as a rule. Recording the context around the object is important because 3D points at the edge of a model are more prone to error than 3D points whose position has been better determined by many surrounding neighbors. We have already seen a lot of general aspects about photogrammetry. Now we want to expand the aspect of photogrammetry to include videogrammetry. In videogrammetry, we work with videos as inputs and require intelligent image selection. With the selected images, we then perform photogrammetry again. This approach has several advantages and disadvantages. The biggest disadvantage is certainly that the individual frames from the videos do not have geotags, which means we cannot perform automatic georeferencing of the 3D models. When we capture individual shots with multicopters, we usually have geotags available and can perform automatic georeferencing during the 3D reconstruction process. However, we will address this disadvantage satisfactorily later on. Let's first explore the possibilities because there isn't just one solution. One possible solution could be to generate a small image set to quickly assess on-site whether a seamless 3D model can be reconstructed using the data. Alternatively, we could express the desire, which is more time-consuming, to obtain the best image set to achieve the most detailed 3D model possible. Here we see, once again, the general 4 rules about recording strategies. We noticed that Rule 2 and 3 contradict each other somewhat. This problem is also called the min-max conflict in videogrammetry. So what's the story behind this min-max conflict? It is certainly logical to assume that we will obtain more 3D points the smaller the image distance is. That is more or less what the rule of 3 suggests on the left side. The smaller the distance, the greater the overlap, and the more points are possible. However, when we look at the practical aspect on the right side, we see that it doesn't work that way. For example, we have a video recording of an approximately 7-meter long wall structure on Galeriestrasse in Dresden, where all the individual frames of the sequence, which were 200 images, were used for a 3-dimensional reconstruction. The point cloud had about 56,000 points. However, if we only use every 10th image instead of the 200 images and reduce the number of images to 20, then the reconstruction provides us with a point cloud of over 500,000 points. This means that we have reconstructed 10 times the amount of points with 1/10 of the images. Let's take a look at the max property and the image on the left side. When we consider the image pairs A and B1 and A and B2, we can see the different image distances between the camera centers. A and B1 are closer to each other than A and B2. The image shows us that a smaller baseline leads to a larger area of uncertainty for a point regarding its actual location. We can conclude that the larger the image distance, the more accurate the 3D points will be, and only accurate 3D points will survive in the model. On the right side, we see what happens when we choose this distance to be too large. False assumptions can arise, or even disjointed 3D models that we can no longer put together. Let's summarize the min-max conflict we need to resolve here. Based on the rule of 3, we can directly derive the min property. The smaller the distance between the images, the more 3D points are possible. However, with the max property, we have another important characteristic which states, the greater the distance between the images, the more accurately 3D points can be determined, and only accurate 3D points survive later in the 3D model. It is clear that if several observers stand around a soccer field and look at a central player, An exact position determination of the player can be made by the different observations. It would be different if two observers standing close to each other see a distant player. By combining these two considerations, we can potentially describe a solution to the min-max conflict. To address the conflict, we need to find a balance between the number of images and the image distance. On one hand, we want to include enough images to capture sufficient visual information and ensure accurate 3D reconstruction. On the other hand, we want to maintain a significant overlap between the images to maximize the number of 3D points. One possible approach is to carefully select a subset of images that strike the right balance. This selection should prioritize images with high feature quantity and quality, while also ensuring a substantial overlap with other selected images. By doing so, we can maximize the number of 3D points while maintaining accuracy and coherence in the reconstructed model. Overall, the solution involves a thoughtful consideration of both the quantity and quality of images, as well as the degree of overlap between them, to effectively resolve the min-max conflict. We typically aim for an overlap range of 80% to 90%. Let's try a simple solution first. Let's attempt a periodic fixed image selection. Maybe we can already solve the min-max problem for a few examples with that. If we don't have any other software available, we can construct a satisfactory solution using the free program Mplayer. If we have recorded a video while moving around an object at a relatively uniform speed, we can use Mplayer, which is available for all operating systems, to extract every nth frame from the video. We can determine a frame interval that ensures at least an 80% overlap and execute the command line accordingly. For example, if we have a video called My Flight and the interesting part starts at 15 seconds, we could extract every 30th frame. If the video has a frame rate of 60 FPS, that means we would extract 2 frames per second. We once tried this exact setup for a video recording in Uzbekistan in 2014. Here you can see the result of the fortress complex in Bukhara very nicely. In the top left, we can see clearly that the multicopter was moving faster in certain paths and slower in others. Nevertheless, the example demonstrates that the simple strategy can indeed work in practice. So far, we haven't made any intelligent decision, but rather extracted every nth frame from a video stream. In the further section, we will go a little deeper into the procedures that are used in videogrammetry. The main focus is on how well two images with similar content match, or the feature sets of both images correspond. When different images come into question, we can move on to include the quality of the individual images. Again, we can say that there is a vast world of different methods that have already been developed, investigated, and utilized. These methods can be categorized under the criteria of correspondence evaluation. There are indeed several mathematical methods in this field, but today I won't delve further into them. These methods originate from autonomous robotics, where similar problems are addressed. Some methods assess how well transformations are found, which can be more computationally demanding compared to other approximations. In our research group, we have also developed a method, depicted in the top right, that can support different strategies, either finding fast solutions or particularly accurate ones. We have also devised a new approach called J-keyframer that provides a reliable measure of the number of potential features on the GPU, saving a tremendous amount of time. Below, you can see an initial glimpse of our visual pipeline in Visual Archeo 3D, which allows for individual configuration and control of 3D reconstruction processes. Let us now compare the advantages and disadvantages of photogrammetry and pure videogrammetry in an overview. If we look at the advantages, the continuous availability of data is a crucial point. Whenever we encounter situations where models are not coming together, we still have sufficient data available for analysis. Additionally, videogrammetry allows for the use of smaller and lighter cameras, and the methodology is more robust compared to the planning required for accurate individual shots and minimizing camera shake. As for the disadvantages, the lack of geotags on individual images is a significant point. This means that automated georeferencing cannot be performed. Videos usually have lower image resolution, so we require much more material compared to photogrammetry to achieve comparable results. Let's look at a few practical examples from close-range videogrammetry. Here we see a videogrammetric 3D reconstruction example taken at Erdene Zoo Monastery in Karakorum in Mongolia in 2022. It is a stone bowl discovered during excavations at the monastery. A Samsung Galaxy S20 was used to capture a nearly 2-minute video at 1080p. Afterwards, 480 images were extracted with JKeyFramer. The top row of images shows the typical circumnavigation of the bowl from different perspectives and with slightly varying distances. Here, strong shadows can be seen between the bowl and the stone below due to the strong sunlight. The lower row of images shows on the left 2 detail shots of the underside, which are well illuminated by the automatic white balance. Next to them are shots that focus specifically on the recess. On the top right, we see the result of the pose estimation in reality capture, and within it, the camera shots on the circling lanes. Below that, we see the result of the 3D reconstruction, which is a very detailed rendering of the bowl. This example shows a stone found during excavation work in 2022 in the citadel of Karabalgasun in Mongolia. A human handprint can be seen on the top of the stone. Here, a Samsung Galaxy S20 was also used to record a video of just under 2 minutes at 1080p. Afterwards, 330 images were extracted with JKeyFramer. On the top right, we see the result in the point cloud after the pose estimation. Below, we see 2 impressions of the 3D model. If we now create a height map of the surface, a so-called digital surface model, or DSM for short, we can make the handprint very clearly visible. After listening carefully to this lecture, answering the following comprehension question should help you to summarize the most important statements again on your own. The practical task is to become familiar with extracting frames from a video.